What's up?
Yeah, I have a question. Can I I have done my library, so
Yeah.
can I check in? I haven't done my library system library my lab.
Yeah.
So I haven't done it yet. So if I do it tonight and checking in the man's office or tomorrow.
Should work. Yeah. Should be fine. I mean, it's due Monday anyway. Yeah, next day of the next lab, right?
Okay.
Yep. Okay. We are just about at Berkeley time, so we will go ahead and get started. Welcome to lecture 20. So a few announcements before we begin. The final project is due Thursday, which is on the 4th of August at 11:59 p.m. The tech spec for the final project is linked in at post 184. Please make sure that you've read that. Remember Professor Hilfinger's golden rule number 3, whatever the assignments, start now. Okay, the in-lab final is soon. That's also on Thursday, which is the 4th of August. It's going to be in your lab section. How do you prepare for that? My advice is to go through past exam problems, as many as you can, and also make sure that you're familiar with the last few concepts we presented. Particularly make sure you understand how dictionaries work, how list comprehensions work, how tree recursion and recursion works, because that's the newer material. So maybe you don't have as much time to practice. So get started right now. Using empty lab sections to your advantage. I think I've spoken about this before, but on days when no new labs are released, you can still use lab sections as office hours. I would encourage you to do past exams if you're done with the rest of your work in your lab, and then ask your TA for their approach to certain problems. This really helped me. It might help you as well, because you might find quicker and better ways to look at problems. Law section 3 is going to be held tomorrow from 2 to 3:30 p.m., not through 4 p.m., because I believe the material will be covered in an hour and a half. It's going to be held in SOTA 306, which is this room. I'm not entirely sure what concepts I'm going to cover, but I think we're going to do a bunch of recursion, and then, yeah, tree recursion for sure, and perhaps go over dictionaries and list comprehensions. I'll look at the feedback form where people put in some of the concepts that they weren't feeling too good about. Okay. So today's lecture, a few words about what we're going to do today. Firstly, whenever you're learning new complicated material, a natural question that arises is, what's the point? Okay, and I think this is an excellent question to ask. Whenever you're learning something new that you find to be, particularly challenging, try to understand why it is that learning about this concept is going to actually help you. So our goal today is to answer this very question, the question of what's the point with respect to dictionaries, complexity, number representation, and time permitting propositional and Boolean logic. So there's these 4 concepts, some of them are new, and I'm going to try to give you a closer look at these concepts and hence define why exactly is it that these are necessary. Okay. So a bonus idea that I wish to communicate today is how all of them tie together. I've been repeating again and again that this class is about understanding your tools well enough to be able to solve unfamiliar problems. Today, we'll also try to understand how these tools work together to help us solve problems at scale, maybe in ways that you're not aware of yet. So before we start, credit for some of the material today, especially the hashing part, goes to Professor Joshua Hugg. He is the vice chair of LSCS, teaches 61B, CS10, probably going to teach CS70, data 100, CS195, so all over the place. Amazing content, amazing lectures. And also Professor Umesh Vazirani. While I haven't borrowed content from him too heavily, my entire teaching philosophy and style is literally just his ideas. So these two are the intellectual forces behind the ideas I will present today. Okay, so let's start off with dictionaries. Firstly, why? Why are we learning about dictionaries? Why are we using dictionaries? I'll start off with the answer that we gave you in the lecture where we presented dictionaries. Okay, so we said dictionaries are a more powerful form of lists. What do I mean by more powerful? Well, the indices in dictionaries are not confined to non-negative integers. Okay, so in a list, all of your indices must be non-negative integers. You start at 0, 1, 2, all the way up until the length of the list -1. But in dictionaries, you are not confined to just using integers as your indices, okay? Consequence is that using dictionaries, you can store mappings or relationships between different data types. You can store a relationship between strings and strings, or perhaps numbers and strings, and so on and so forth. But is that all? Is that the only reason that we're using dictionaries rather than just lists? And if it is, I'm not impressed, okay? And here's why. What do lists do? In one way, lists also map integers to different data types, in the sense that each index has an item that it contains. So it's mapping an index to the item that it contains. So in some ways, lists are already providing us a mapping. And let's see an example of this. Suppose I have a list that contains the strings TA, instructor, and reader. I would say that this list represents the mapping 0 to TA, 1 to instructor, and 2 to reader. And can I see thumbs if this idea makes sense? Okay, so it's mapping the index of an item to the corresponding item. Great. But what about dictionaries? Well, dictionaries map data types to data types. They map objects of certain data types to objects of the same or other data types. So if you had a dictionary like A, the key A referring to the value TA, the key B referring to instructor, and so on, it would represent the mapping A to TA, B to instructor, and C to reader. Can I see thumbs if this makes sense? So it's a mapping between a key and its corresponding value. But then, can't we just make a dictionary out of lists? Are dictionaries just two lists used together? Because think about it. Suppose I have one list, okay? And we're looking at our previous dictionary. My first list contains all of the keys of the dictionary. So it contains A, B, and C. This list provides a mapping between its indices and the keys of the dictionary. So 0 maps to A, 1 maps to B, and 2 maps to C, okay? And then I'll make another list. Now this list contains the corresponding values in our dictionary. So 0 maps to, the 0 maps to TA, 1 maps to instructor, and 2 maps to reader. Can I see thumbs if that makes sense? The last line is a little bit off, but I think, okay. Let's actually fix that right now. So 0 would map to TA, 1 would map to instructor, and 2 would map to reader. Okay, can I see thumbs if it makes sense now? Excellent. Okay. So my idea now is, why don't I just take these two lists, find the index of the key in the first list, and then just give you back the item at that very index in the second list. And in essence, what I've done is I've just mimicked a dictionary. Do you see why? Suppose I wanted to find in my data structure the value contained at item B. What I can do is I can look at my first list and I can say, B, where are you? Well, B is at index 1. Excellent. All I need to do is return the value or the item at index 1 in the second list. And I end up getting back instructor and problem solved. I'm taking in a key and giving out a value. Can I see thumbs if this makes sense? It's rather interesting, right? So using two lists, we can implement a dictionary-like data structure in Python. So let's do that. I'm going to open up some code that I've already written, and let's try to understand what the code is doing. So first, I'm creating my first list, which is the keys list. Then I'm creating another list, which is the values list. And I'm also defining two methods. My first method is called add pair. It takes in a key and it takes in a value. To the first list, it adds my key. To the second list, it adds my value. As a consequence of using the append method, both the key and the value are added to the end of the list, which means they will be added at the same index. Can I see thumbs if that makes sense? Any questions so far? Okay, then what's happening? Well, I define another method called find a value, which takes in a key. It loops through the first list, the list containing the keys. It finds out what index that key is stored at, and then it returns the item at that index in my second list, in my values list. Because all the keys and all the values are stored at the same indices, this code works. But let's say the key didn't exist. Well, in that case, I can just return not found. Can I see thumbs if that made sense? Okay, any questions thus far? Okay, so then let's try to look at this code in practice. So I have this file or this interpreter shell I've started here. And basically whatever code I just showed you is the code that this shell is going to be running on. So I'll show you one more thing that I've done. What I've done is I've looped through all the numbers from 1 to, what is this? 1, 2, 3, 4, 5, 6, 7, 8, 9. So 100 million. Okay. So all the numbers from 1 to 100 billion minus 1 have been put into this new data structure that I have. And how have I put them? Well, I've put each number as a key and I've put the number plus 1 as a value. Okay. And now what I'm going to try to do is I'm going to try to find a particular value in this data structure. So let's do find val1. Okay, it gives me back 2. It seems to be working. How does it work? Well, it goes through the keys list. It sees in which index the key 1 is. It looks into that index in the values list, and the values list has a value that is just 1 more than the key, which is 2. So it returns 2. Can I see thumbs if this makes sense? Oh, okay. I thought this might be confusing. Let me just do it anyway. I have a list called keys that has 1, 2, all the way up until some really large number, I think 10 to the 8 minus 1. And I have a list called values where I have the corresponding values, which are just 1 more than the corresponding key. At each index, I store these key value mappings. Can I see thumbs if this makes sense? Excellent. So let's try to find another value. Let's try to find the value 1000. Pretty instant. Gives me back 1001. Okay. Let's try to find this value. You will notice that as and when I try to find larger values, the code takes more and more and more time. Okay. So right now, as I try to find the largest number possible, it took about 7 to 8 seconds to execute. So as my values kept increasing, so did the number of seconds it took me to find that particular value. Let's look at an alternate way to implement this very thing. Let's look at an actual dictionary. Okay, so a built-in Python dictionary where we have dict is equal to an empty dictionary. I'm adding all the numbers as keys in this dictionary, and as values, I'm adding 1 plus the number. So I'm doing what I did with my 2 lists, but this time I'm using an actual dictionary. Okay, and we'll see what happens. So in this second version, where I'm using an actual dictionary, let's see what happens if I do find val1. Okay, works relatively instantly, just as the first one did. What about find val 1000? Okay, that's also super fast. It works instantly, no lag yet. What about find val 1,000,000? Wow, okay, that also worked instantly. It gave me back the correct value. What if I keep blowing it up until, the thing is not in the dictionary, I get not found instantly. Can I see thumbs if you've noticed the difference in time it took to execute the same calls in both structures? Okay, so you notice how dictionaries are much, much quicker than just using my 2 lists, even though the same task is being accomplished. I'm giving it a key and getting out a value. If I use lists, it takes a long time. If I use dictionaries, it's constant. Okay. Is CS a scam? Yeah.
That question about the previous one.
Yeah.
So like the runtime, is there a difference because we are using the 2 list in one, or is it because like something built in Python?
Well, we are going to answer that question soon. As it turns out, 2 lists rather than 1 doesn't really make too much of a difference, because sorting through 1 list might be linear time, and then you just have 2n, which is the same thing. Okay, good question. Turns out it's not. Okay, and I've kind of shown you why. Because the dictionaries actually operate much, much, much quicker. So I've answered the first question. The first question was, why are we giving you dictionaries when you already have lists? Now, the next question is, why does this work? Why is it quicker? So let's have a look. recall that when we presented dictionaries to you, we also gave you a set of rules that we just asked you to follow. It was pretty hand wavy. We didn't explain the rules, but we said, just learn them for now. The first rule was keys should be immutable. Why is that? You don't know. Keys must be distinct. Why is that? Well, you don't know the real reason. Dictionaries are faster. Why is that? We have no clue. Now, the answer to all three of these queries lie in this topic called hashing, which I will try to introduce today, okay? Hashing is a brilliant technique that we can use to store sets of items. So in this case, I was trying to store a bunch of numbers. That's a set of items, so I can use hashing. Hashing relies on something called a hash function. A hash function is a function that takes in a single item and computes a unique integer value for that item. So it may take in my name, give back a unique integer. It may take in someone else's name, give back a completely different integer. And since this is harder to understand with words, I have a diagram here. So consider this. There's this large set that consists of every possible English string. Okay, so the word dog, the word instructor, the word weather, the word soda. And now we have this neat little function called h of s, which takes in a word and computes a unique number associated to that word. It's almost like taking in your names and giving back a student ID. No two people have the same student ID, okay? Can I see thumbs if this concept makes sense? What the hash function is doing. Excellent. So now the idea here is that for any key passed into a dictionary, the unique value that this hash function can compute can simply become the address where that value lives, okay? And now this might be, again, a little hard to visualize, but let's, or a little hard to imagine, but let's look at the consequence of this. Firstly, given a key, we don't need to scan through anything. The hash function tells us immediately the place in memory where its value is stored, okay? And how does it do that? Well, like I said before, you have a set of all the strings. The hash function gives you a number. Let's just treat that number as an address and store the value of that key at that particular address. What this means is that anytime I give a key, all I need to do is call the hash function. The hash function will tell me the address in which the key's value is stored. And I go there and I pick up the certain value that I'm looking at. I don't need to go through every single value or every single index in a list. It's similar to, an analogy of, suppose we were to ask you to find Soda Hall, and it's the first day of class, you're like, okay, where's Soda 306? And we told you it's somewhere in California. You would have to run through the streets of Berkeley, go crazy to find Soda Hall. But if I gave you the address, or if I gave you a link to the exact coordinates on Google Maps, you know exactly where to look. So you don't have to waste your time sifting through different streets or different values. Can I see thumbs if that analogy makes sense? Great. So what we have just done is we have taken a problem where you can have millions and millions of items in a list, and you can find one particular item instantly. You don't have to look at anything. We have a question. Sorry? Yes, it will. And I will cover that also in one of our slides. That's a good observation. It certainly will take more memory. Okay. So now that we understand how dictionaries are really, really working, let's try to answer these three hand-wavy questions. The first question was, keys must be immutable. Well, why is that? Think about it. If I change a key, the result of calling the hash function will also change, right? If you take a key and hash function always returns a unique value for any key, then it'll return a unique address where the value is stored. Now, if you change the key, the hash function will not be able to give you that address back because the address is unique to every single key. Can I see thumbs if that makes sense? So consider this. Suppose I'm trying to store the word bat, okay? My hash function has a unique number for every single word possible. So it takes this word bat and it gives me the address, let's say 27. I say, excellent. I go to the memory address 27 and I store bat. Now, all of a sudden, I found some way to change this value. I changed the value to cat. Okay. And now I try to find it in my memory. What's going to happen? Well, the hash function will look at cat and it will give another unique value. Why? No two words can have the same value. So perhaps it gives us something like 28. And then I go into my memory and I look at 28 and I don't find anything, right? And I get lost, which means I have now lost that address forever. So there's no way that I should be able to change my keys, because otherwise there's no way for me to find the corresponding values. Can I see thumbs if that made a little more sense? Excellent. The next thing was that our keys must be distinct. Why is that? Well, the hash function computes a unique value for every unique key, okay? So if two keys are the same, then of course, the result of hashing them will also give you the same value. The hash function, when called on the same object, will always return the same value, which means we have a problem. Because which item lives in that memory index? The item belonging to the first key or the second key? We have no idea. So our keys must be distinct, since distinct keys get mapped to distinct locations in memory. Can I see thumbs if that made sense? Okay, dictionaries are also faster. What was that? Okay, so dictionaries are also faster, and you've already seen a demonstration of why, but let's look a little bit closer at that result. Okay, so as I said, we went from, and I've used theta here. You don't have to worry about that. I just put it there because I wanted to throw the term out. We went from theta n to theta 1 in our worst case. Think about it as we went from big O of n when we were looking through the whole list to big O of 1, because we knew exactly where to look. And the difference was crazy. We shelled approximately 7 to 8 seconds each time we multiplied the value by 10. Okay. But what if our lists were much bigger? Let's think about another solution. Let's say instead of linearly looking through the whole list, I used binary search instead. Now you might remember from labs that binary search actually works in log n time and linear search works in linear time worst case. What's the difference though? Are they really that different? Let's have a look. But before we do that, my question to you is, can we always use binary search? Why not? Any other hands? Okay, Jeevan.
It will only work on a sorted list.
Okay, it only works on sorted lists. Any other ideas? That's the premise of it. Binary search will only work on sorted lists. But what does it mean to sort a list? It means that for any two items in a list, we must be able to compare them to each other, right? If you're sorting a bunch of numbers, well, you can compare them by value. But what if you're sorting a bunch of names? Okay, maybe you can use the dictionary order. What if I create a class dog and I ask you to sort a bunch of dogs? It's interesting. What if I have a list of functions? How do you sort functions? You can only use binary search if the items within your data structure are comparable, right? So that's another caveat to keep in mind. But let's assume that the items are comparable and let's see what happens. Suppose that our list contains, or our data structure contains e to the 8 items, which is 3,000 items. If we're searching linearly, of course, we must look 3,000 times in the worst case. What if we're using binary search? Well, it turns out we must only look about 8 times. Why is that? Remember, the bases of the logs don't matter, and I'm using log base e. So if I have e to the 8 items, and my algorithm takes log base e of n time, where n is e to the 8, well, then it's only going to take 8 searches, right? And I'm done. A dictionary will only take 1. Now, what if I square the number of items that I have? Now I have a list with 10 million items. The linear search will have to look 10 million times. The binary search will only have to look about 16 times. So there's a huge difference here between logarithmic time and linear time. It's not even comparable, but the dictionary will only take 1 search because it knows where to look. If I had a billion items, I would have to search a billion times. With linear search, I would only have to look about 30 times when I'm using my linear search, my binary search, and my dictionary will only look once. Okay. So I think you've seen these numbers before. So let me put it into context. Suppose the population of the world is 8 billion. For every single person in the world, I've stored their name. Imagine everyone's name is unique. If I search linearly through this list, and it takes me 1 second to look at a name, I'm going to take 260 years before I get through and find a certain name. If I use binary search, it'll take me 4 minutes. Okay, 260 years versus 4 minutes. If I use a dictionary, it's going to take me 1 second. And that's insane. These numbers are crazy. Okay, my question to you is, what happens if I use a nested for loop? And I go through the whole list, comparing each element to each other element pairwise. But it turns out the universe will end before the program computes. So it's actually crazy how much these little shifts, and seemingly little shifts, because we only look at it as log n squared, and we only used to using small numbers, but they change the power of computing. They change the scale of the problems that we can solve using the tools that we have. Now, do you see why big O of n plus 4 is roughly the same as big O of n? In numbers so large, it barely makes a dent. If you're looking at 10 billion things, you may well look at 4 more. It won't make that much of a difference. Can I see thumbs if these numbers help you understand why we drop constants and factors? Okay, and does anyone have any questions about that? Okay, so the takeaway idea is that whenever we're looking at runtime, we're thinking about problems that are exceptionally large. So we really don't care about these constant factors or anything that you're adding, a constant that you're adding or subtracting. Okay, but then there's a question. How do we define such a hash function, right? Like I very neatly said that, oh, I have a function, takes in any string whatsoever and generates a unique value for me to store stuff. But then where am I getting this function? Let's think about it. Recall by our definition, a hash function is a function that provides a unique integer value for a given English string. And I'm confining it to English strings because it's just easier to present that way. Okay. In other words, we are converting a set of digits or characters to an integer representation. In other words, a base 10 representation, going from alphabets, which is its own representation system, to base 10, which is our preferred representation system. Does that ring any bells? It certainly should, right? Number representation, the concept we taught you this week. What is number representation? The practice of representing values using different symbols, right? Values are fixed, values are constant, our symbols keep changing. Okay. Strings can be thought of as values. The string dog is different from the string cat. Okay. Remember the definition of the word base. The base in number representation simply refers to the number of digits that are available in a representation system. So if I have the English alphabet and I map every single letter to their corresponding index. So A is the first letter, so it gets 1. B is the second letter. Z is the 26th letter. Then I just reduce the problem to this whole problem to converting a base 26 number to a base 10 number, right? That's about it. And you've seen how to convert binary. You've seen how to convert hexadecimal. In discussion, we also talked a little bit about how to convert arbitrary bases. So then how might I solve this problem? Well, consider the word reader, okay? I can convert the word reader to an integer simply by using base 26 representation, where I multiply each alphabet by the base to the power, the index in which that alphabet appears in the word, or the position in which that alphabet appears in the word. Well, what does it mean to multiply R by 26 to the 5? Well, R is just the 18th alphabet. So I can multiply 18 by 26 to the 5, add to it, well, E is the 5th alphabet, so 5 times 26 to the 4, so on and so forth, and I end up getting this large number, 2161700076. My claim to you is that using such a system, the representation that I get for any word whatsoever is unique. No two words will ever result in the same numerical value, given that there are no spaces, by the way. Do keep that in mind. I'm saying words, I'm not saying sentences. And if you'd like to know why, you should take a course in number theory. But I'll give you an analogy. In our base 10 system, can you represent the same value 2 different ways? Certainly not. If you have a value 1010, The only way to write that is 1 0 1 0, assuming we don't have trailing zeros in the beginning. Okay. Similarly, there's no way you can represent a certain value in a base 26 system in two different ways. So that solves our problem because we've defined the hash function for any string of English letters. And what we've done now is we've computed a theoretical basis for being able to store any word in the English language and be able to retrieve it in constant time, which is insane. It's what, an 8-week class in programming, and you've solved that problem. Okay. But there's more. That's not all there is to these concepts that we're showing you. And what I want to show you is a very, very cool application of binary numbers that a friend of mine actually showed me. And we'll go back to the XOR problem from your midterm. And my claim to you is we can solve this XOR problem using a combination of number representation and Boolean operators. So and, not, or, so on and so forth. Okay. My first claim is the entire truth table for the XOR block can be representing using two binary numbers, both of which are 8 digits long. Okay. And let's recall what the XOR function actually was. The XOR function takes two Boolean values. It returns true if both the values are different, and it returns false if both the values are true. So let's think about how we can represent that using binary numbers. Well, here's an idea. Let the number 1 represent a true value and 0 represent a false value. Consequence, all possible inputs to the XOR function can be representing using this number 1100 1001. Can anyone tell me why or how this actually makes sense? This is certainly a hard question, but just throwing it out there. If I treat 1 as, yeah, Zoriana. Perfect. Absolutely perfect. That's it, right? The only possible combinations of true and false values when I'm taking two values at a time are that both are true, both are false. One is true, the other is false, and one is false and the other is true. So let's look at that. 1 1 represents the scenario when both inputs are true. 0 0 represents the scenario when both are false. And then 1 0 and 0 1 represents the scenario when one is true and one is false. Okay. Now, given these inputs, I want to convert them to the Boolean number 0011. And why is that? Well, in the first instance, when both are true, when we have 1 1, I want the output to be false. So I want the output to be 0. In the second instance, when both are false, when I have this second 0 0, again, they're both the same. So I want the output to be false. I want the output to be 0. In the third instance, where I have, and third and the fourth instance, where I have different values, I want the output to be true. So I want the output to be 1 in both cases. Can I see thumbs if you understand how this binary conversion represents the XOR problem? So some of us are nodding. I would prefer thumbs because it helps me quickly count. Excellent. Okay. So let's think about it. Let's think about how the solution we provided to you actually works. Let's use our operators on every single pair of these numbers. Before we do that, let me write out the solution. So A XOR B, where A and B are two Boolean values, is the same as not A and B and A or B. And why is that? Well, both of them certainly shouldn't be true, and at least one of them must be true. Those two statements in unison imply that one must be true and one must be false. Can I see thumbs if you somewhat remember the solution and this makes sense? Does anyone want an explanation for the solution? Okay, so we're feeling good? Okay. So let's look at that solution in the context of our binary numbers. So we take the first pair, which is 1 1, and right now we're only doing the first half of the work, which is doing not A and B. Okay. So we'll treat the first one as A, the second one as B. And we're going to say not 1 and 1, since A is 1 and B is 1, which is the same thing as saying not 1. Why? Because 1 and 1 is true and true, which is just true. But since trues are 1, we convert it back. And so we end up getting 0. Do you understand this step? Because if you do, you'll be able to understand future steps. If you don't, raise your hands and I'll try to clarify this. Okay, so let's clarify. What I have said is that 1 represents a true value and 0 represents a false value. Now I'm looking at these two numbers, 1, 1, and I'm trying to do the operation not A and B, where A is 1 and B is 1. So then what happens? Well, I replace A by 1 and I replace B by 1. Let me start by doing just that. So not 1 and 1. Then I realize, well, 1 just means true, right? So I'm trying to do not true and true. What's the result of true and true? It's just true, right? Because both values are true. So I get, well, not true. And what's not true? Well, just false, right? And what's false? Just 0 in our representation, but 1 is true and 0 is false. So this ends up going back to the 0 value, which is why not 1 and 1 just becomes 0, because it's the same as not true and true. Can I see thumbs if that made a little more sense? Excellent. Okay, so then let's proceed to the next case. Well, not 0 and 0. 0 and 0 returns 0. Not 0 is 1. Simply replacing these with trues and falses. Okay, what about 1 and 0? Well, not 1 and 0 is not 0, which is also 1. Great. What about 0 and 1? Same thing. The AND operator does not care about the ordering of its inputs. So we end up getting this thing, 0, 1, 1, 1. But we're not really done yet. We've only done the first half of our solution. But let's remember our result. Okay, our result is 0, 1, 1, 1. And let's proceed. So the next thing we're going to do is we're going to remember our result and then use it here in the AND A or B case. So we're doing 0, 1, 1, 1 and A or B. So let's focus on A or B. Well, what's happening? Okay. In terms of the 11 case, the first pair, 1 or 1 is just 1, because true or true is just true. In the second case, when both inputs are false, which means both are 0, we end up getting a 0. Third case, 1, 0, we end up getting a 1, and 0, 1, we end up getting a 1. Can I see thumbs if that made sense? Excellent. So now we end up getting this result, 1, 0, 1, 1. So my result boils down to 0, 1, 1, 1 and 1, 0, 1, 1, right? And what's that? Well, 0 and 1 gives me 0. 1 and 0 gives me 0. 1 and 1 gives me 1. And 1 and 1 gives me 1 again. And my result is precisely what I needed, which is 0, 0, 1, 1. Now, this is, to me at least, a ridiculously clever application of binary numbers, right? If I were using base 10, this really wouldn't strike me. Or at least I would find it much harder to think about how I can represent two values distinctly. But in terms of binary notation, it's just implicit. It's given to us. You're either 1 or you're 0, and there's no other choices. So using my binary operators, I can actually solve any truth table or any Boolean value or any Boolean problem whatsoever. Can I see thumbs if you're satisfied with that claim? Happy with that? Yeah, question. No, I will post them after lecture. Yeah. Any other questions? What? Yeah. Oh, I didn't say it though.
Okay,
I'll say it. Yeah. There was a question? Yeah. Oh, really?
I'll fix it.
Thank you.
Yeah.
Any other questions about the self-check or otherwise? So the self-check for this lecture is not really like, it's not super complicated. It's just asking you like 4 questions. The first one was just who was lecturing, so we can make sure you actually hear or you watch the recording. The second one was what's the time complexity of trying to find a value in a dictionary? Does someone want to answer that? Yes. Constant time, right? Because of hashing, what we saw. We know where to look, so we must not waste our time looking anywhere else. The third question was, what's the time complexity of indexing into a list? What do we think? Or sorry, not indexing into, the time complexity of finding the index given a certain value in the worst case in a list. Any ideas? Yep, Cynthia. Perfect. It's linear. The fourth question was, to understand recursion, you must first understand. Yeah, you like the second option? Okay. Any ideas? What's the answer? Never seen it before? Does someone want to shout it out? There we go. Recursion. Perfect. You know, there's a second. Yeah. Zoriana. You sure?
I'm just gonna ask.
Uh-huh. Absolutely. What would you like to explain? Why it's constant time? Yeah. So let's actually tie that together. That's a good way to summarize what happened. So the procedure here was, given any key for a dictionary, when we're trying to add the key in, I take my hash function and I call it on the key. The hash function called on the key returns a unique integer, which I use as my address. So a unique address. Now, once I've taken this key and I've stored its value at the unique address, the next time when the user tells me, hey, can you find the value related to this key? I take that key, I call the hash function on it again, I get back the address, and I just go look there rather than sorting through the whole stack or the whole memory. And I find my value there. And if the value doesn't exist, I return not found instantly. Does that help? Awesome. Any other questions? Yeah. Oh yeah, for sure. From the first value to 0011. Yeah. So, oh, oops. Would you like me to start at the beginning where I did this, the not A and B? Yeah, for sure. Okay. So what I did was, for every pair of digits that I had in the larger value, I applied my first half of the solution, which was not A and B, by treating A as the first value in the pair and B as the second value. So for 1, 1, I said not 1 and 1. Then I just treated ones as trues. So 1 and 1 is true and true, which means it just becomes 1. And then I did not 1, which gave me 0. Does that make sense? Okay. So then I applied that to every such pair, and I got back 4 digits, 0, 1, 1, 1. And that was the solution to the first half of my problem. Great. And then I had the second half where I had to do and A or B. Okay. So I did the same A or B operation to every single pair, and I did 1 or 1 is 1, so on and so forth. Does that part make sense? Okay. And then the result of this was 1, 0, 1, 1. So I got back 1, 0, 1, 1. And the last thing I had to do is AND them together, because I had not A and B and A or B. So for this last AND, I just pairwise ANDed them together, and I got 0 and 1 is 0, 1 and 0 is 0, and then 1 and 1 is 1 for a result of 0, 0, 1, 1. Does that make sense? Awesome. Any other questions? Okay. Okay. So a few takeaways from this lecture. Problem solving is actually beautiful, because so many times what happens is, we lose the forest in the trees, which is because problem solving is also exceptionally hard sometimes, right? You're learning all of these tools that we're throwing at you. We're expecting you to master them and then testing you on them, which can be rigorous. But I would really encourage you once in a while to zoom out and to try to really understand these tools, understand how they work together. Go online and look at a few examples, make these connections. I mean, it's easier to say for me, but with time, it does happen. Why are we using binary? Ask such questions. And then you will find that there are actually really well-developed connections with everything, and they really gear you towards solving larger problems efficiently. Okay, that was all I had for today. Thank you. Thanks so much. Thank you. Appreciate it.
Right.
Thank you. Mm-hmm. Yeah. That's only if I use binary search, right? And binary search assumes that the list is sorted, but in the workspace it may not be. Not constant because it is exactly. Yeah, yeah, sure.
Oh, there you go.
Yeah, no, I actually, yeah. I'll find the office hours right after this, so you can attend the office after.
Are they?
I forgot the annual meeting.
Oh, can you put your slides on the website from yesterday too? I know